Right. So the best way to think about what we're doing is to think about it as the next frontier of agriculture. Okay, and it's agriculture on the sea for sustainable feed, food, and energy. And if you know, there's a little history behind this and I can tell you more. But the way when we started on our journey about 11 years ago, it was more about, hey, how do we create sustainable biofuels for the planet, for India in particular, because we're such a large country. And we don't have any fuel of our own, any crude oil of our own. So we said, oh, but we also are a signatory to the Paris Convention. And so how do we kind of get all this together? So a few of my students, and I was a professor at, I retired and decided that I was actually going to go back into academia just to have some fun with my students. And so a few students got together, and they had about a year and a half before they were going to graduate. And we said, hey, why don't we kind of work out the math on what this biofuel would look like? And it turned out that, if we, for example, India imports about 250 million tons of crude oil. Now it's the third largest energy consumer. And if we wanted to make all of that from as a biofuel, roughly when you work out the energy density of biomass and crude oil, you get to see that it's basically you need about 4 times the weight of biomass. So that's about 250 million tons into 4, and that's about 1 billion tons of biomass. Now, a billion tons of biomass was almost like the entire agricultural output of India. So, I mean, so what do people eat then if we were to divert all that biomass into biofuel? And that's really what got us thinking. Because what is agriculture ultimately? Ultimately, agriculture is about capturing the sun's energy into a form of biomass. And then that biomass can be used for a variety of things, including feeding ourselves. So we all live off the sunlight because, whichever way we look at it, that biomass we either eat it directly if you're a vegetarian, or if you feed it to cattle or to poultry, and then we consume that. So directly or indirectly, all of us live off sunlight. And so we said, okay, agriculture is what actually allows sunlight to be picked up. So why don't we pick it up over the ocean? Because there is the earth is 70% water, and there is so much there's only so much land, and so maybe we could save all that for feeding our growing population, and then for our energy needs, wouldn't it be wonderful if we could pick it up over the ocean? Now it turns out that when we start framing the problem in that way, if you look at this little map of the world, much of the sun's energy falls in the tropical regions, and that's reflected by the temperature of the water. The redder, all the red zones that we see, they're the warmest waters in the world. And so we said, are there tropical sea plants that can grow? And of course there are in the temperate, in the tropical regions, and of course there are. And in fact, they've been grown for a very long time. And these sea plants, these tropical red sea plants, are extremely promising. First of all, not just because they've had a long history of farming. These are the sea plants that are used to make agar and carrageenan and many other food ingredients. But they also have a very high growth rate, and they have a very short growing cycle, not a season, a growing cycle, which means if you plant the sea plant in the water, within 45 days, it has grown to about 4 or 5 times its original weight. And then because the tropical waters are more or less similar, the same temperature throughout the year, there is a possibility of year-round growth of these sea plants. Now, when you come to think of a industrial raw material, what is the real characteristic of an industrial raw material? The fact is that you want a raw material to be available to you uh, uh, 24 7 365 in the year, right? I mean, that's what really allows a factory to really function efficiently. Now, most agriculture, as you can imagine, is seasonal, and here you have an industrial raw material that is potentially available throughout the year. So that was super exciting. And then it turned out that it's not, these sea plants can be grown in a tremendous area. All the green area that are marked out for you is actually the area that's available for growth. And all the red dots that you see are areas where in scientific literature, the growth of these tropical sea plants that I talked about in the previous slides, basically these strains of Capophycus, Eucuma, and Gracilaria, they grow very well and they've been reported. So this was super exciting because, hey, we have a potential biomass, a large growth area. So what's really holding this back? Well, we figured out that the agriculture on the sea, the way it's been practiced right now, is very, very manual. And while sea plant cultivation has a lot of advantages in terms of year-round availability of biomass, the fact that it's so labor intensive makes the price of the biomass quite high. And that limits the applications to which this biomass can be applied. So while we could show that the biomass itself was extremely versatile, you can make it's practically raw material like for a biorefinery. One can start with agricultural inputs. You can make feed additives, organic chemicals, biofuels, plastics. So there's technically nothing holding it back except the economic viability. So that was quite interesting. And when you look at agriculture as such, compare sea agriculture and land agriculture, what would happen is that in land agriculture, we have many input costs. So first of all, there's a cost of land. If you had the land, then there would be the cost of irrigation. Then there would be the cost of fertilizer, and then there would be the cost of labor. If you looked at sea agriculture, there is really no cost of land. I know, and land is, the sea is available in plenty. There is no cost for irrigation water because there's plenty of seawater. There is no cost for fertilizer and other nutrients because whatever nutrients the sea plant needs, it's already dissolved in the seawater. Sunlight is free, the carbon dioxide is free. The only input is labor. So if we could mechanize this, perhaps we could bring it down. And I'm going to speak a little bit more about it. But as a company, we have to survive. We have to make money. So what we started our journey with was, we said, what are the products that we could commercialize right now? And as we build up all the systems in the future to bring down the cost of the biomass, so we can open up many more areas. So what the products that we've commercialized right now are actually mainly a product for agriculture. So what we discovered that these sea plants have a unique chemical composition, this tropical sea plants. And if we isolated certain fractions from there, and that is a story in itself, how we got around to isolating these fractions, we found that these fractions actually have a profound impact in stimulating the growth of plants. So today, in agriculture, there are two major classes of inputs. One is fertilizer, which we're all familiar with, and the other one is insecticides and pesticides for that. So we found that we could make these biostimulants. So we created products and commercialized products for agriculture. And we've also shown that we could make products for animal health and for food ingredients. And, we can convert the sea plant biomass into bioplastics and biofuels as such. But as I said, we are a startup, we are a company. So, you have to focus very strongly. And just to give you an idea of how large even the agriculture markets is, just the biostimulant market itself is more than a couple of $1 billion. We have another product that we've made which for agriculture, which can stimulate the immune systems of plant. The plants actually have an immune system and actually reduce the amount of pesticide and insecticide that plants use. Then there is the food ingredients market. There's the animal health market. So you're talking about just for these products alone, even without counting all the bioplastics and biofuels, more than a $10 billion market, enough to keep us busy for a very long time. So that's what we've gotten started on as a company. The biostimulant, which goes under our brand name of AgroGain, is actually now been tested in many different countries, and we're selling it with partners like FMC Corporation and Summit Agro, with more than 20 different crop types, and it just keeps growing. So this has become a big product for us. This is actually what allowed our company to actually start making good revenues and actually break even. What does AgroGain do actually? What do these biostimulants do? Well, it turns out that the mode of action, and we understand the mode of action of these biostimulants, it upregulates the many pathways in typical plants, which increase nutrient uptake, which upregulate photosynthesis, cell division. So as a result, what happens is when a farmer applies a biostimulant like AgroGain on his or her field, the increased yield that they get for the same amount of inputs, no more fertilizer, no more water, no more labor, no other input. They just get extra yield from their fields for the same amount of input for using the biostimulant, because the biostimulant allows the plant to use the existing inputs far more efficiently. So as a result, based on the crop, you can get yield increases from, say, anywhere between 10% to even more than 25%. So for example, in sugarcane, we get at least 25% yield increase, rice, maize. So these are all the cereal crops. We get similar yield increases in vegetable crops, such as in the second row, and also in fruits. So, I mean, over a wide variety of crop types, basically. That's all I'm trying to say. So now the farmer itself, the farmer can get the return on investment by just the yield increase. So if a farmer uses $1 worth of the biostimulant like AgroGain, they can get $4 to $5 worth of extra yield crop. But the amazing thing that happens is because all of this happens, for example, in maize, you get a 10% yield increase. All of this yield increase happens for no extra input. So one gets an extra biomass in the field, which ends up capturing an amount of carbon dioxide that wouldn't normally have been captured by traditional means. So we made a calculation. While growing the sea plant biomass in the ocean itself can capture carbon dioxide, its usage on the crop actually amplifies that carbon dioxide capture. And we figured out that we made these calculations based on field trial data in a corn field. This was done in Ohio. We could capture more than 5,000 tons of additional carbon dioxide for every ton of the product that was used. So that's very exciting. And, people ask us, wow, this is great. But, when are we actually going to see biofuels and bioplastics, from sea plants, which is what is going to truly replace it? Well, the first thing is it possible? And it turns out that one has to use a very special process called hydrothermal liquefaction. This is a process that runs at high temperatures and pressures. And it's a process that is specifically suited for wet biomass. And one can take the biomass and, it's kind of an acceleration of the process that happens when land biomass goes down into the earth and, cooks slowly for millions of years. You can just speed up the whole cooking process by increasing the temperature and the pressure. And one gets at the end of it, basically a crude oil. So if this kind of biocrude could be produced on a large scale and could be produced cost effectively, the implications are enormous. for the implications are that one could take existing oil refineries and maybe feed them with bio crude derived from these kind of sea plant based raw materials. And at the end of the day, whatever one gets from such refineries would all be renewable. So one could get renewable gasoline, renewable diesel, renewable organic chemicals, you name it. So, I mean, that's the real potential, because one can take the sea plant biomass and make biocrude. Now, the other interesting thing we found is this: the sea plant biomass by itself is a natural polymer. And so one could, well, we've already demonstrated that we could make biodegradable sheets, pouches, bags, even straws from just processing the sea plant biomass, this tropical sea plant biomass, in different ways. That's an enormous possibility. In fact, the issue is today for us is that it's extremely biodegradable, and sometimes one wants it to be a little biodegrade a little less slowly, because if many of the nice properties of plastics are all derived from the fact that it's hydrophobic. And so these are some of the issues that we are working forward to. But to make all this happen, we need to be able to bring down the cost of biomass, especially biocrude and bioplastics. So how do we plan to make that happen? So it's important to understand how sea plants are cultivated today. And it's, as I mentioned before, it's extremely manual, labor intensive. And on the left is a picture of sea plant cultivation in Tanzania. And on the right is a picture of sea plant cultivation in Indonesia. You can see that the people walk out into these shallow and calm reef areas. So right beyond where the arrow is pointing, you can see the surf breaking. So all this is the shallow and calm reef area. People have planted sea plants on these stakes in the sand. So it's kind of planted like, you take a bit of the biomass, you plant it like a flower garland, you stretch it between two stakes, leave it in the seawater. 6 weeks later, 45 days later, it's grown back to its original size, repeat the process. And here on the right-hand side, you can see the same process being done in Indonesia. It's very labor intensive because you can see on the picture on the left, this is a bunch of sea plant that has just been harvested. And these women are basically taking small bits of the sea plant, tying it on these blue strings. Here is a similar operation happening in India. And then once the bits of sea plant are tied on the string, it's put out into the sea. 6 weeks later, it's grown to its full potential, 4 or 5 times its size. We put it back into the process here and starts again. So you can see that apart from labor, there is hardly any other input cost. And also the sea plant cultivation is limited today because of the areas in which it can be grown, shallow waters and calm waters. So at Sea6, we studied this process, and we understood, and we said these are the 2 limitations that we need to remove. How can we speed up the mechanization? And so what we did was we invented machinery, and this is all published patents, and we put it together in a boat, very inventive name, Sea Combine. And what it does is that it automates the whole process of harvesting the seaweed from the sea, breaking it up into smaller pieces, and seeding it back and laying back all of that into the ocean. So that's really what the Sea Combine does. And with the Sea Combine, we are now able to visualize large scale, low cost. So here is the prototype of the Sea Combine and the waters of Bali in Indonesia. And on the lower side, on the picture at the bottom is actually a drone shot of many seaweed farms laid out offshore, these are the kind of seaweed farms that the Sea Combine can actually work on, harvest, and so I mean, it's technically possible. So as we improve the labor productivity on the Sea Combine, we're not only able to get more biomass per person, but we're also able to lower the cost of biomass. So I mean, if we had to lower, for example, the cost of biomass by a factor of 10 from current production costs, and with the mechanization that I just showed you, we could actually lower, say, get a factor of 100 productivity. We could afford to pay each person working on the sea 10 times more and still manage to reduce the cost of biomass tenfold. So that's the journey we are on. And if you see this red line is the current economic viability. Here is where we are today with our first stage of mechanization. And within 4 to 5 years, I believe with when we implement our mechanization fully, we should be within shooting range of biofuel, but definitely we should be able to make renewable bioplastics, chemicals very cost effectively. So that's really what our journey is about, how to use a renewable biomass like this tropical biomass, very versatile, available throughout the year, able to grow in large quantities, and then convert it into all these renewable chemicals and feed additives. We started about 11 years ago, and we started thinking, and so we've had some time to actually build up this technology platform. If you look at the kind of technology that Sea6 Energy has, you can broadly classify it into two buckets. One is about being able to produce the biomass in large quantities and low cost, so-called biomass production systems. And that's where the Sea Combine comes in. We have other concepts called floating islands, which allow us to work offshore and which are covered by patents. On the other side, the chemical composition of the sea plant biomass is literally like nothing on land earth. I mean, no other land plant has this kind of chemical composition. For example, this is a polymer of galactose. It's very rare to find polymers of galactose in land plants. And plus, this is a lot of salt in here. So, we've had to develop unique processes to be able to convert this biomass into useful products. And that's covered by a set of patents as well. So that's really, we have this platform technology, but as a company, we have to focus very sharply because you can't spread yourself so thin. This is a very big concept. So our first phase has all been about getting a couple of products to the market. We've just managed to raise funding, and now we hope to substantially increase our attention on in the next 4 to 5 years would be definitely food ingredients, feed ingredients, and hopefully we'll get to, we'd really like to do bioplastics as well. So that's what the summary of our company is about. So I would say we can revolutionize the ocean-based economy. As a company, we're about 60 plus full-time equivalents, most of them engineers, biologists. Our main research and development headquarters are based out of Bangalore in India, and we also have a production facility in the south of India. We have an additional production facility in Bali in Indonesia, and that's also where our Sea Combine is based. And that's essentially about our company. My own experience, as Olia mentioned, I mean, I was in the pharmaceutical industry, chemical engineer, more than 25 years, decided to call it a day and went back to teach. And this is where I met my co-founders, who were my students, and one thing led to the other. And, they're all my partners in C6. I mean, we keep very busy. I mean, and what's very exciting is that everything that we naturally do tends to fit into all of these sustainable development goals that have been laid out by the United Nations. I mean, it's just by doing what we do, we can fulfill all of these goals. So that's also pretty satisfying, while we are also a viable, economically viable company, and hopefully will make that difference to the planet. I mean, that's what our company's vision is about: disruptive solutions for a sustainable planet. So I'll just stop sharing at this point of time and get back to the screen if you have any. There's a whole load of questions. Wow.
Actually, we're going to use the hands up mechanism as well, because they were coming in throughout the talk. So in case those questions were answered, we'll do that. So first of all, everybody unmute yourselves. All right, please clap for this amazing, super inspiring talk.
Thank you.
The best we can do online. Awesome. Now, folks, please raise your hands, and if people could, whoever is in the position to do so, please turn your cameras back on. I think it's a little warmer that way. So yeah, let's see. Yeah, please use the raise your hand option, and then we'll, if there's still time, we'll take that from the chat as well. So Alok, why don't you go ahead?
Hi, Shri. I'm also based in India. I just relocated a month ago, so it's great to be here. And so tell me a little bit more about biostimulants. What are they?
So biostimulants are a very new class of agricultural inputs. So traditionally, as I mentioned earlier, agriculture is practiced with two major kinds of inputs, fertilizers and insecticides and pesticides. So our approach to agriculture has always been, let's feed the plant. Here's, like a whole lot of food for the plant, fertilizer, eat. And then there is, in case the plant has a disease, then you kind of shoot the invader. That's been our approach to agriculture. But, plants have been around for millions of years, much before we came along. So what biostimulants do is that they improve the nutrient use efficiency of the food that's put in. So they improve the uptake of the fertilizer. Typically fertilizer use efficiency is roughly about 30 to 40%. So in other words, if you put in 100 kilos of fertilizer, we all work metric here, okay? So if you put in 100 kilos of fertilizer, only 40 kilos gets used in any typical agriculture. About the bulk of it is degraded, wasted, runoff, whatever else in that limited growth period. So what biostimulants do is that they upregulate the uptake mechanism. So in the same growth period, the first thing that happens is more fertilizer is sucked into the plant. So the genes responsible for active uptake are also upregulated. But that's not just enough. What does the plant do with all of the extra nutrition that's coming? So what biostimulants also do is upregulate photosynthesis and cell division. So energy fixation and cell division. So when you put all of this together, that results in more biomass in the same growth period. So it's not magic, but it's a very new way of improving efficiency. So that's actually being now recognized as a third important category of agricultural inputs. So it's been known that there have been many materials that can somehow produce this agricultural efficiency increase, but nobody really figured out how they were acting or the science behind it. And what we've done at Sea6 is, for example, in folklore, seaweed biomass has been known to improve agricultural efficiencies. But those are all temperate kelps, and the chemical composition of temperate kelps is very different. What we've done at Sea6 is that we've actually figured out what precise fractions are acting, and they're very different kind of chemical composition from temperate kelp. These are more sulfated galacto-oligosaccharides, and how they act, what genes they upregulate. And this is really what biostimulants are all about today. So that's one category of biostimulants. The other one that I mentioned briefly is plants have what are called an innate immune system, just like any other living system. So if we catch a disease or if we have an infection, there are two approaches that we take. One is we take an antibiotic. If it's a bacterial infection or a fungal, we take an antibiotic. So that's like killing the invader. But there is a vaccine approach, right? Which we can stimulate our own immune systems to prevent the progression of disease. And plants have such a similar immune system. And these concepts are just getting recognized in agriculture. They're a different kind of stimulatory effect, but we have, so these are the two major products for agriculture. Hope that answered your question, Alok.
I'm sorry, I have to butt in here for a quick clarification. is this like, do you coat the seed in it, or do you like spray it on it when it's like a little plant? What like how would,
Okay.
say I'm pitching this to a farmer, how would they use it?
Yeah. So it's a very good question. So one can use foliar sprays, and one can use drip irrigation. So
Mhm.
these are the two main ways, or in-furrow irrigation. So these are the different ways in which farmers apply their inputs currently, whether it's a pesticide or a fertilizer. And because the labor involved in applying these materials is significant, so our materials are extremely compatible with existing sprays. So you can just add the stuff into your existing spray regime, no extra labor, just the extra benefit.
I'm a little confused in the sense that if this is so important, then why doesn't fertilizer already come with this? Like the assumption is that fertilizers are
Yeah. So the regulation for biostimulants is just getting off the ground. Okay. And Europe has actually put forward its biostimulant regulation. India has already passed biostimulant regulation. The US is still in the draft stage. I mean, I think it got stuck in the last 4 or 5 years for several reasons. So so yeah, it's if you look into the agriculture domain now, this is one of the hottest areas. Biostimulants is one of the hottest areas. Okay. Right.
Awesome. All right, folks, if anybody has a question, do raise your hand, but I'm going to start taking from the chat now. Stanley, do you want to ask your question?
Yeah, I'm just scrolling back up because it's been a while.
If you still have it, no pressure.
Yes, I think I found it. So basically my question, I asked 2 questions, basically thoughts about unintended consequences to the ecosystem, like due to, let's say, over cultivation, adding on to Alok's question, as well as the cultivation areas, like if, let's say, the sea level rises a meter, 2 meters, a couple of meters, how would it affect the available cultivation areas for the plants? So it would be great to hear some commentary on that. Thanks.
Okay. So the current manual method of cultivation is restricted to waters that are maybe at the most 6 feet, 2 meters to 3 meters deep, because more than that, it's very uncomfortable for people to walk out at high tide. I mean, and at low, and more than that, it's pretty uncomfortable for people to work in the sea. So what we have managed to achieve with the mechanization systems is depth is not a constraint anymore. Neither is using, and some of the systems that we use to anchor the sea plants in the water, they're capable of withstanding very rough water. So literally, when you go out into the sea, right now we are cultivating in waters of more than 100 feet, 30 meters deep. And literally, we think that if there's nothing to limit us from going to even 100 meters or more. It's just the cost of anchoring. So to answer your question, therefore, if the sea level were to rise, what that would affect is the amount of available land area. But as far as sea plant cultivation is concerned, especially our kind of sea plant, we're not affected. In fact, we see this as a fantastic opportunity for small island nations whose real wealth is the enormous amount of sea around those islands, and whose wealth is actually the sunlight that falls on the sea. Okay, so so I think this is where it's likely to grow. I mean, I foresee that. I mean, even if you take the United States has a lot of tropical islands, say the Pacific Islands, for instance. Okay, and today they could all become, in the future, I hope, fuel producing stations, biofuel producing stations. And you can even visualize ships making this journey across the Pacific and stopping midway for refueling with completely renewable fuel. Why not? I mean, it's entirely possible. Okay, it's just how much do we want to do? How much can we achieve in a few years. So we're planning to slice this cake and completely chew it properly, you know. But it's a huge opportunity for the world.
Thank you, Eric.
Hey, I think I wanted to ask maybe the opposite question, which is what's the short list of the ecosystem benefits of having more seaweed out there? For example, there's folks in California working pretty hard to reduce the urchin's impact on the large kelp forest here. But I'd be interested in what benefits just having more seaweed out there, near shore, deep water, near mangroves, not near mangroves.
Right. So obviously, the more plants we grow, the better it is for the environment, because they inherently capture a lot of carbon dioxide. And especially if you grow them near shore, they also sequester a lot of the runoff from human activities. You know, all the fertilizer, all the eutrophication that otherwise happens is captured by sea plants. So that's a real advantage of growing sea plants. Most of the kelps, and especially of the coast of California, and all the kelps that you see, they are rooted plants. In other words, they have to, you know, they have a hold fast equivalent to a root system, which has to anchor onto the sea bottom, and then the plant just grows straight through. So in one sense, they are also limited by the depth of the sea. Kelps can't grow in very deep water, for instance, very, very deep water, because sunlight does not penetrate that deep. The kind of sea plants that we are talking about don't need hold fast. They are vegetatively propagated. So, you know, as long as they have a piece that's available, that's you know, it can multiply, vegetative propagation. But the disadvantage is that they need to be supported, because they are they're heavier than water, so their natural habitat is actually shallow waters, not more than 20 meters deep. So because they sink to the bottom, and then they are very happy to stay on a rock and grow, even though they don't need to hold on to that hold fast. What we have done is we have invented, if you recall the picture that I showed about the sea combine and the sea, we have invented structures that can float near the surface. And therefore, the structures are now depth independent. So you can literally do farming in areas where farming was not possible before. As a result, you know, we can sequester more carbon dioxide, pick up more nutrients, and use those areas of the sea, and, you know, save the foreshore areas, or the nearshore areas for other human activities. You know, if you want to go to the beach and you want to enjoy your day on the beach, the last thing you want to see is seaweed farms off the beach, right? I mean, so we can really literally work over the horizon and have all of those benefits, and it can be a win-win situation. Okay. So many, many benefits, not just direct benefits, also indirect benefits. Like I showed, the biostimulant growing the seaweed to produce biostimulant has a direct benefit in terms of the amount of carbon dioxide captured. But the biostimulant itself can accelerate land crop growth, and that has a further amplification effect on capture of carbon dioxide. So besides reduction in fertilizer usage, and, you know, today all fertilizer is made from fossil fuels. Mm-hmm. So many benefits.
You'd also mentioned that you lose like what, 10% to fish, 10% of the biomass to fish.
Yeah. Like that's true. I mean, like any other agriculture, you know, there are opportunistic natural prey, natural pests that, well, you can't call them pests. You know, they also have to survive. You know, like you do land agriculture, you'll lose some of your crop to birds and, you know, insects. So the same happens in the sea. If you grow a crop in the sea, there will be folks living in the sea that, you know, say rightfully turn up for a free meal. So you just have to live with it, right? You just pay your fish tax and you live with it. Okay, thank you for visiting us. Here's your free meal. Now let us alone.
Sounds like the fisheries people will thank you for that also.
It does make a difference, because these are actually it's quite well known. You know, when you have large structures out in the sea, they aggregate, they attract fish, because fish like to shelter there. Okay, from there. So it's called fish aggregation devices. So you can actually increase fish catches in and around seaweed farms. Yeah.
Awesome. Julia, I think your question's next.
Hi there. Sorry, I can't turn my camera on right now, but I wanted to, hear more about your relationship with farmers and how they've received this type of mechanism and kind of what your strategy for employment is.
So the whole idea is that there is a lot more biomass that needs to be grown than there is available today, and at a much lower price. So in our strategy, we have to lower the price of sea plant biomass. And the way we do that, and of course, as you can see, the sea combines and other mechanization also need some people to operate. So our strategy is to improve the farmer productivity by using the mechanization by a factor of, say, 100. One farmer can do 100 times more than what they're doing right now. So that increases the amount of biomass available. At the same time, because they're producing 100 times more, they can also maybe get a 10 times higher income for that, and at the same time be able to reduce the price of biomass by a factor of 10. So this is the way the equation we'd like the equation to work out. In practical terms, it's a little bit like the invention of the tractor or land agricultural machinery. So today, sea agriculture is literally in the Stone Ages. You know, it's like trying to do agriculture on land with a pick and a hoe or even a sharp stone, versus today what you can do, what one person can achieve with a tractor, combine harvester. So the machinery is just being introduced. And so we do most of this work in Indonesia, because Indonesia has very well worked out laws for leasing the sea for doing this kind of aquaculture. And so we work with farmer communities, villages, and that's really, it's not just science here. So we have to take the whole community along with you. They have to see the benefit, because it is people from these communities who will support us when we try and do our farming. So that in case we choose to do our own farming. In the future, we also see models where we could take and give out our equipment like to farmer cooperatives who can then grow the sea plants for us. And then, we can, there's so many mechanisms that need to evolve. So it's absolutely new. But taking the community along with us has been, that's been our prime focus. And there is no other way. There is no other way.
Great, thanks so much.
Audrey, you're next.
Hey there. Thanks for what you're doing. Super cool. I am friends with a company that is partnered with an Alaskan company that grows wakame on ropes. So I guess Indaria. And from the photos I've seen, it looks huge. Like that stuff grows super fast in the summer. So even, I don't know if it's a hold fast seaweed. It seems like they're able to cultivate it. Yes, with labor is a huge input. But if you're just shooting for biomass, it seems like cold water kelps just like go bonkers in summertime at least. Trade-offs between, I guess, investing in more cold water infrastructure since they grow so fast versus maybe the tropical seaweeds, which are slower. And then, of course, the thing there is, well, the only thing I've heard those being used for is like food and maybe fertilizer or animal feed, but not in sort of the ways you've outlined with your seaweed, where there's like a clear like percentage benefit or something. So are you aware of more research on cold water kelp, or is it sort of an area that needs work?
Oh, no, no, no. There's a lot of work going on cold water kelp. In fact, it's too little work going on tropical seaweeds. In fact, far more on cold water kelp. The science is full of research on cold water kelp. Undaria, the species that you mentioned, is primarily used for food. It's a holdfast type of kelp. And you're right. In the Arctic regions where there is enormous nutrient concentrations, the kelp just goes crazy in summer, right? It just, so we've done those calculations. So overall, I think on an overall, if you were to look at biomass productivity per hectare per year, I would say that the cold water kelps are just as good as tropical seaweed. Okay, so there's no in terms of overall biomass productivity per hectare per year. The issue, however, is that the kelp um, grows very fast in the summertime, and there is a huge mega crop somewhere late autumn, right? And the rest of the year is barren. Okay. From an industrial perspective, there are two issues with that kind of stuff. One is when the crop comes, you have to figure out how to store it. Okay. And because if you want our factories to run throughout the year, you need a steady supply of biomass, not just one whole pile of biomass. Now, that problem has been handled, right? I mean, agriculture is also seasonal. For example, in the northern hemisphere, in the temperate regions, we have just one agricultural season, right? Late autumn, people harvest, and then life has been going on. You store your wheat and you store your cereals throughout the year and run it. Whereas in the tropical regions, agriculture happens 3 times a year. Okay, in India, for instance, there are 3 agricultural seasons. So storage is particularly difficult if you have wet biomass. So all of these kelps have more than 95% water compared to land-based biomass like maize or wheat or rice. They're far drier. So you dry them a little bit, you can store them. But wet biomass starts fermenting in no time. So that's a huge challenge. Therefore, if you see, and if we have a biomass that's 95% water and 5% solids, the amount of energy that's needed to dry this biomass and the amount just is so huge that it'll dwarf the amount of energy that you can finally get from the biomass. Okay, so unless we use solar energy to dry it, which is free, but then you need a lot of area, you're back to the same equation. So they do have a great growth rate, but we have to figure out how to deal with these issues, or figure out how to keep these wet biomass stable in containers for a long time, so that they can be used over a period. So these are problems to be solved. The Arctic and the Northern Hemisphere regions are extremely rich in nutrients, very rich in nutrients. The tropical oceans are very poor in nutrients. Okay, they're rich in sunlight. So one way around this is that it's difficult to bring sunlight to the Arctic or the Antarctic, but it's easier to bring nutrients to the tropic. For example, one fact that's very well known is that beyond 100-meter water depth, the so-called aphotic zone, where the sun rays do not penetrate anymore, those waters are very rich in nutrients, nitrogen, phosphorus, and potassium. So the future of ocean farming in the tropical regions would be upwelling these nutrients to surface ocean farms, okay, and to be able to harvest these nutrients. So one can visualize this enormous amounts of protein, nitrogen in the deep oceans, okay? So if we could actually upwell that, and upwelling is not, is proven, I mean, and it's done, and the question is, what do you do with the upwelled water? People have been trying to grow plankton. Instead, if you can feed tropical sea plant to farms with upwelled nutrient-rich water, not only could we have more carbohydrate-based biomass, we could grow even species which are nitrogen, which are protein-rich. So one could probably even solve the protein problem for humanity, the nutrition problem for humanity, rather than just the energy problem. So there are many possibilities. This is absolutely a place where many more people need to work. Okay.
Well, thanks.
I think this is the best agricultural supply chain answer I've ever heard to anything. Alok, do you want to go next?
Oh, I can wait. I can wait if anybody else has a question in the chat.
Ivan, I think you may have been next on the chat queue, if that's still relevant.
Sorry. Yes. Thank you very much for the talk, and congratulations on building something that has survived for more than 11 years. That's a credible accomplishment right there. I was curious, this is more back on the ecosystem impacts of what your algae and seaweed cultivation. Are the species you're cultivating in these areas endemic to those areas, or are they non-native? And then I was also wondering if you could speak a little bit about, is anything displaced when you cultivate at an industrial scale, and do you monitor the ecosystem, for example, the number and type of plants and animal species? I mean, I know you mentioned fish are attracted for the shelter that algae and seaweed provide, but I didn't know if there were, that was displacing something else.
Okay, so there are several questions in your question. So let me just try and sequentially answer them, because these are questions we get very often. Okay, let's talk about, I think let's talk about the displacement of, are we, by growing sea plants, are we displacing anything else that might have grown there? So the tropical oceans are basically deserts, okay? Like I said, they're sunlight rich, but they're not nutrient rich. And the reason they're not nutrient rich is because the moment there is nutrient in these sunlight rich areas, in these warm areas, biomass just grows quickly and depletes all the nutrients. And then all of the nutrients sink back to the bottom of the ocean. Okay, and that is why we have such a huge accumulation of nutrients at the bottom of the ocean. So the tropical oceans are deserts. These sea plants have learned to adapt to the ultra low levels of nitrate and phosphate that occurs in the surface of the tropical oceans. They're incredibly, they're almost pure carbohydrate fixing machines. Typical, if you take a Arctic kelp, for instance, or a cold water kelp, including the macrocystis that grows off the coast of California, or the kelps that somebody was talking about, Undaria, in the northern regions, the grow of Korea, Japan. Seaweeds are normally considered protein rich, but, and those seaweeds can go up to as much as 15, 20, even 50% protein. Whereas the seaweeds that I'm talking about, the tropical seaweeds, you'd be lucky if you cross 4% protein. It's basically a carbohydrate fixing machine. So nature has optimized these sea plants to survive on very low nitrogen waters. But it's not that if you start pumping nitrogen at them, for example, upwelled ocean water, they will become from 4%, they'll go to 15% protein. But somehow they learn to survive at 4% protein. So therefore, one answer to your question is that we're trying to grow plants in a desert. Okay. So what happens when you start growing plants in a desert? So imagine a land-based desert where nothing is growing, and then we start, some good soul goes and starts planting that desert with species that survive. So the moment you plant a desert, you create an ecosystem. Okay, then you have birds, insects, stuff coming in, and then there's for some reason the organic matter of the content of the soil goes up. So many things happen over a period of time. So this is precisely what happens when you go and start planting deserts in the ocean. Okay, it's so, in other words, as far as we see, we are not taking away anything. We are actually creating. It's like kind of planting forests in the sea. Now, in terms of the species that get attracted, I mentioned the fish, but we've also seen turtles. And then along with the fish come bigger predator fish who tell each other, hey man, there are all these small guys out there, if the moment they come out of the seaweed farm, we can feast on them. So you end up creating a whole ecosystem. Okay. So that's really the way it works. We're always asking ourselves this question. So what is there anything else that can are we by intervening, are we going to cause some difference? But so far the answers have always been positive, and we keep thinking about it. And if we come up with something, surely I can't imagine that there'll be any activity of human beings that's completely benign. So I'm pretty sure that so far it's been encouraging.
That's great to hear. And
Well, we're on the sharp lookout for all of this stuff. I mean, as much, and if there's anybody brings anything to our notice, by all means, of course, we'll have to mitigate those effects. I don't know what those are, but we'll have to mitigate them. So, okay, thank you for the question.
excellent.
It has been an hour, so I do want to make sure that we're very respectful of your time. We do seem to have infinite questions, so if you have more time, we'll keep shooting those questions at you. But
Yeah,
if you don't,
I can take about 10 more minutes. So
yeah,
then
yeah,
take a
thank you
break.
so
Okay?
much. All right, Sean, do you want to go next? Maybe not. Let's try Doe, and then we can go back to Sean.
Hi. Yeah, just the same question I asked in the chat. Being curious if someone is interested in the seaweed industry, especially on the business operations sort of side, how they would get involved. Can you hear me?
I just happened to lose my internet, but I think I'm back up. Could you repeat that question, please?
Sure. I'm just curious if someone's interested, especially on the business and operations side of things, how they could get more involved in the industry generally or in your organization.
So our industry, apart from the fact that we get our raw material from the sea, our industry is no different from any other industry. In the sense that our raw material is unique. It comes from the sea, and so there are operations involved in farming the sea, just like agriculture. So that's just the raw material. But once the raw material comes into the company, it's like any other raw material. Like we have our normal factories, which processes raw material to whether it's biostimulant or biodefense or biopolymers or whatever else we choose to. And those are all just your classical operations with all the classical problems, with all the people issues and all the cash flow issues. And, it's not going to be any different. So I think the short answer to your question is that, yeah, there will be new knowledge definitely in farming the oceans and managing large farms, and also some new processes to convert these this new raw material into traditional products. But it won't be this, there will always be scope. We're all normal people, came from normal backgrounds, so we just had we all learn, so there's no problem. Anybody who's willing to learn can learn. They don't teach the stuff at college yet.
Yeah, no, I guess my question was more like, I agree with that. And what is a good contact point for getting involved?
Like, hiring maybe is the question.
Are we hiring? Okay.
Thank you.
Yeah, I mean, we are. I mean, in the sense that, as I said, we're only about 60 plus people, and we just have to grow. So you can reach out to me on LinkedIn, and we can see what the opportunities are. But it would, because our headquarters are based out of India, and Indonesia is where the tropical regions, obviously our focus on most people would be people willing to relocate and work here at the moment. I mean, we don't mind, we love talent from all across the world, but even in Zoom times, there is some physical stuff that needs to be done. It probably get done out of India and out of Indonesia. We do have an intention to we are marketing our stuff in many parts of the world. And the other thing that we are doing is we are collaborating, because this is such a huge problem to solve that we need the best talent from all over the world. So in short, the answer is yes, we are open, but I'd say it has to be in a where, when, how specific, and it has to work for the person coming in. It has to work for us. And I think that's just the honest answer.
Mhm.
Great, thank you so much.
Sean, I think you're up next.
Yeah, hey, you talked about upwelling to get more nutrients to seaweeds in the Caribbean regions or the equatorial regions. How do you see the pros and cons of upwelling as opposed to like depth cycling or something like that, where you're looking at more mechanical means and potentially deeper depth farming methods?
So by depth cycling, I presume you mean taking the whole farm down to a depth where it can absorb nutrients and then bring it back up again, and do
Yeah,
that.
exactly.
Yeah. Well, in our specific context, given the floating structures and the engineering that's associated with that, it would be a very complex problem to sink the whole farm down to 100 meters deep, then raise it up again. With all those cables and everything intact. So it would be a far simpler problem to bring the nutrients up. And the reason I say that is because if, just from a simple perspective of physics, imagine the nutrient upwelling pipe to be just like a long straw going down 100 meters into the sea, assuming that we are farming in an area where there is deep water right underneath and this nutrient rich water. Imagine that it's like a long pipe going all the way down. The hydrostatic pressure inside and outside the pipe is the same. So if from within the pipe, we just keep pulling out water from the top, the hydrostatic pressure on the outside will keep upwelling the water automatically. So there's very little energy that is required. You don't really, one really doesn't have to pump up water from 100 meters deep and against it. So there's very little, just keep taking off the water from the surface of a long pipe and, the hydrostatic pressure will upwell it. One does need some power for that. And in the middle of the sea, one of the inventions we've done is a kind of a floating solar. So a floating structure, it's called a tensegrity structure, and we can put floating solar on that. That generates enough power to run a small pump under a motor. And of course, the power is only generated during the daytime or when the sun is shining, but that's when the plants need the nutrients, So you upwell during the time the plants need the nutrients and, they're able to use the nutrients. And then in the night, anyway, the sun goes down, so the upwelling can stop, but then the plants don't need the nutrients because there's no light to do photosynthesis. So that's the general broad concept of how upwelling could work. But honestly, this is work in progress. There is a lot of experience in upwelling, but we have to marry. I think it would be great to just collaborate with someone who's doing upwelling and, not to have to reinvent the wheel. But let me put it this way, even without upwelling, there are many natural upwelling zones. We call them the Goldilocks zones, okay, where the sea is just fertile. I mean, you just have to go and plant it there. So, I mean, we haven't exhausted them yet. So but yeah, there's
Great.
a lot of stuff.
Appreciate
And
it.
speaking of Sea Energy, Marcus, do you want to take the last question? No pressure.
Yeah, no, definitely. Have you looked into using other renewables like waste power, for example, for upwelling? And I'd love to chat some more. We might have a pump for you that is ocean going.
Could you repeat that again, please?
Have you looked into other renewables like ocean energy, like waste power for upwelling?
Sure. I mean, I think we should be power agnostic. Power source agnostic. I mean, it's just that that's not our area of expertise. So as long as there is any other source of renewable energy that can upwell water, why not? I mean, I'm very open. So I'd love to hear more about that. Okay. I must say that this upwelling and this very large ocean farms out there in the middle of nowhere is not something that is actively that we are planning to do in the next 1 year. Okay, but this is something that will come into our research program in the next 3 years. We have the concepts and we have the basic protections around that, but we have more biomass now than that's we have to figure out how to absorb all that biomass. So in other words, we'll have to really completely make all the bioplastics, all the properties of the bioplastics, and that creates a huge demand for the biomass. Okay, and that's when you really want to go out and farm. Right now we have our Sea Combine is working in near shore or just not even over the horizon, maybe a couple of kilometers offshore, is able to provide a lot of biomass for the moment.
Wonderful. Well, thank you so much. Thank you for taking all of the questions. This was incredibly inspiring. Now everybody unmute yourself one last time. Some clapping.
Thank you very much. Honestly, I love the questions, and it's always a pleasure to talk to people who are excited and interested in these areas. Thank you very much for the opportunity.